Okay, so this is a talk that I'm going to present to you on a localization technique developed completely in-house in a former project of mine by a very talented team. We were deploying drones in warehouses for the inventory management use case. A couple companies out there are working on this. We were developing an in-house solution. Um, Got the idea to present at the PX4 Dev Conference because I think there's a lot of nice tie-ins to the PX4 ecosystem. You're going to see some familiar names. The general problem in warehouses in general is that they're losing like a lot of inventory per year, like billions of dollars, and that's just going to continue to increase. And the thesis, you're going to see like a lot of companies, they're using robotics to help address these challenges. So typically, a couple companies out there using drones. We were one of them. Another couple companies using ground robotics. It's a very, hot space right now, right? So really cool use case. Definitely advise people to check it out if they want to see dull, dirty, dangerous real world use case with applied robotics. And the capital is there to invest it in and find drone platforms. So this talk is going to present on SAVLoc, which is the shorthand notation for Structure-Aided Visual Localization. The short of it is we were using the structures themselves in warehouses to do our localization. It wasn't a full SLAM approach. And you'll see I'll kind of call mine to it. We had started with April tags. We were building this solution at a former project, Cientis, which was an internal venture at a larger company, Nokia. We were using voxel 2-based drone platforms for the actual cycle counting task. We had made this selection because of the swap advantage that it provided, so size, weight, and power. I'm just going to call out, no matter how solid you tried to convince a potential customer your autonomy routines are, definitely helps if you can make some claims about the overall safety of the system from like first physics principles. So low mass, low power. The modal platform had always been very good for us, right? And we looked at a couple others as well. Smaller was often better when trying to convince customer to deploy this in warehouse with forklifts and people. We use PX4 as the flight control stack. So we had a low-level geometric control approach, which I won't cover in this talk, but that we integrated directly to the attitude control layer. So we had actually started just using the full cascaded PID, but then eventually when we wanted tighter performance, went deeper. So PX4 providing hooks at each of the levels was very beneficial for that. It made the planning for the roadmap on when we were going to do that very efficient. ROS-based application stack. So we were actually using ROS1. I probably shouldn't say that, but we were. That wasn't the most important part, based on how we had designed the software. Is really just out of pure convenience. We could have migrated to ROS2 eventually had we needed to, but it's just hard to, you have some legacy software, you don't want to throw it away. It finds its way in. And we had actually started with April tags for this. So, a lot of robotics use cases actually start with April tags because they're cheap and easy and the dictionaries are quite large. But, we were targeting 100,000 square foot warehouse or more, and your April tag deployments depending on the density, can scale to the thousands very quickly. So we were looking for a solution that would scale, that from like an operational perspective, so minimize the number of touch points, and then customers also generally liked if you didn't add any physical infrastructure. So of course you can convince them that you can, and a lot of solutions out there that work with it. Okay. So just an overview of the algorithm. There's three main stages. There's an image processing stage with rectification, some semantic segmentation of what's being seen, and then we would extract boundaries and features. Then a structure correspondence stage. I'm going to go through these in more detail, where we were trying to figure out effectively of the possible structures in the area of the camera, which ones were we actually looking at in the very large warehouse. And then the final stage where we're actually estimating the 6 degree of freedom pose from these outputs from the former two stages. The pipeline itself that we were using to implement this algorithm, there were actually two generations to it. So the first generation was actually a split architecture where we would package an image or a stream of images and localization requests to like a very basic interface like off-board. We had like an edge server running on the local prem if we could use the customer Wi-Fi. If we couldn't, we would often just have like a little laptop running an inference stage you'll see in the structure course, or the image processing stage. There were definitely some bottlenecks on the hardware that we use, as Voxel 1 was old. So some temperature compute bottlenecks, some network bottlenecks as well. Actually worked pretty well when the network was working, although in general, definitely advise for any like low latency autonomy requirements or routines, just try to run it on board if possible. Less, things that aren't latency sensitive, you can kick it out to the cloud and come back and it's generally going to be okay, but be careful with, autonomy routines. Second generation, everything was completely on board. So the Voxel 2 had plenty of compute. We were running it around 1 to 2 hertz for the SAVLoc detections. So you can imagine, you saw the GIF in the first slide with the drone flying around the tower. It's just basically opportunistic every time it sees a horizontal or vertical member of the shelving. Try to get a correction, and we're trying to correct for the drift that accumulates in the visual odometry algorithm that the modal platforms had typically shipped with. Okay, so a couple assumptions and priors for how we were building this. There was a mapping stage, although it's a bit different than a typical mapping stage. When we would onboard a customer, we would work with them to get effectively their floor plan, which is the layout of where all the structures are for every rack that we might need to go fly in the facility. And generally, there's a handful of configurations that racking structures might take in a warehouse that are very regular. Layouts. Quite typically, the worst place that we had was a very small warehouse with 30 different rack configurations. That was a bit of a nightmare because you have to, for this technique, as you can imagine, you're trying to use, you need to know the geometry of a specific rack layout, right? But it's a tractable problem. It can be done, it can be known ahead of time, and you can actually go in and measure it, and assuming that they built the warehouse to spec, which is, if they didn't, that's a big problem actually. You can generally trust it, right? I mean, you can accumulate a couple centimeters of error, but it's not terrible. And then the other assumption, once we had the map built, was that generally shelving configurations wouldn't change. Although on occasion, right, you'd have, a forklift driven into like a warehouse structure and it would bend it like all to hell. So, you'd have to maybe account for that or just remove it from the map. You could go in and kind of easily detect these because you'd get your log the next day and you'd see something weird had happened and you'd localize it to a specific area. Okay, first stage, image processing. So the goal of this is to transform raw image instead of geometric primitives, so effectively lines and corners. Tried to make this, as visual as I possibly could. You'll see kind of later stages gets a little bit, just kind of cheated and put all text. First stage we're going to do is rectify an image, generally a good first stage when doing any computer vision processing. The second step in this stage was generate pixel-wise segmentation maps. So we used YOLO V8. We had a custom model. We trained it on about like 6,000 images, which doesn't actually take that long to accumulate and to, kind of train on. If you have somebody just sitting there or a team of people kind of doing the annotations and there's services out there that can do it. And effectively what you would get is, it may be a little hard to see, but you can't see my mouse either, but you would get these little masks on like the racking structures themselves in that third picture. And then the third step in this is we would try to fit lines to the edges of all of the masked regions. So all of the distinct, unique masked regions, we would like just use a technique like ransack or something and try to find what is the best fitting line segment in the 2D image plane to the structure that we think that we detected with the mask, right? So false positives can be a problem here, but in general, you can kind of train that out, and as time goes on, things tend to stabilize. Second stage, the goal is really to then try to figure out what 3D structures are we looking at, and try to make a proposal on that and apply some checks to make sure that, yeah, it's probably, we're looking at vertical 3 and section 5 in the southeast part of the warehouse. So first step is we're going to project map features into the image just using the prior pose. So you can use that prior information to figure out roughly for a given radius around the camera, these are probably the structures we were looking at, and projected into the image, they would, have these line segments. You kind of see that hopefully in the second. We would compute matching costs. So for all of the segments that we had found, we would compute a cost to match them to the segments that were detected. So we have two like working groups here, and then we would solve it basically as a a Hungarian algorithm, so linear sum assignment problem to figure out what was the lowest cost way to match the two sets. And typically we would do this in two stages. Verticals match first, just helps to constrain the set of what we're going to look at in the second step when we look at horizontals. Generally, this algorithm can also be flexible if there's only a vertical in the field of view or only a horizontal as well. You can do some things where you can just use some prior information and kind of crank up the uncertainty about some of your measurements, but works best when you have both. And then generally, we also, at each step, one of the ways that we added reliability is we would try to validate matches right at the end of each stage, rather, before we propagate the data into the next stage. So we could look at geometric and prior pose plausibility. So, kind of check that the geometry that would result from the projections that you've now done the matching for, would it actually make sense in reality? Like, have you said that you have a horizontal beam next to a vertical beam, right? That have to happen, right? Also the prior pose can give some constraints based on how fast you generally let your drone fly through your warehouse, which was not that quick. We tried to be safe. Okay. Third stage. This one is just more pure math, so I just kind of kept it to text. Apologies, but in this stage, we're trying to solve for the final 6 degree of freedom pose. We do have, you can use some assumptions just about the real world geometry as well. Generally, horizontal beams are, parallel to the ground. Vertical beams are perpendicular. When you end up with like the underlying like deeper mathematical like implementation for this, you get like these systems of equations that you can actually simplify using those things, because when you project those 3D structures into the 2D plane, as you move along, like projected features, for example, like it has to all correspond to like a specific 3D member. So just trust me, you can apply some simplifying assumptions, and generally what we would do is we would first recover rotation. So we would use the vanishing point geometry. So if we think that we found like a good candidate vertical member, we would use the vanishing point location to figure out what the pitch was. You could determine yaw candidate from the horizontals, and then generally roll can just be derived from with the resulting matrix constraint. So just take the cross product of them if you want to. For estimating translation, we kind of do this in two stages as well. So we try to derive like a good scale constraint for the depth from the tower structure. Because of that mapping stage that we had initially, and because we can pretty confidently say we think it was this specific beam, we can actually take the pixel wise measurements, do a little bit of math with the known thickness, and kind of get an estimate of the depth. So yes, it is sensitive to potential like noise and like pixel level measurements. But generally, if you can get a very good segmentation mask, you can actually kind of mitigate that a little bit, and it's not a huge issue. And then once R is fixed and we have a strong depth constraint, we would typically then solve for the translation. So we try to just use like a least squares approach to find the best fit for potential set of candidates for the translation vector that would reproject back onto the image to match the correspondences that we had. If only like one of the two types of structures was visible, we may constrain the pose using like prior estimates as well, and just crank up the covariance to make it trusted a little bit less in that axis. And again, before we would take the content or the output from this, we would validate it and we would fuse it. So again, we would just check to make sure. You could do like a geometry, like a reprojection check, just to make sure everything checks out with the real world geometry again. The integration with PX4. So since we were running on top of it, this is how we had generally approached it. We actually put an extended Kalman filter or a linear Kalman filter. It depended based on which implementation or how we were feeling. I think it started as a linear, and then we eventually went to extended. But we would actually fuse the SAVLoc measurements with what was coming out of whatever VIO algorithm was running on the modal platform, and then we would feed that into the PX4 layer as like an odometry message. So I think a pretty typical, external odometry estimate into PX4. It's a little different than the native implementation on like the modal platforms, but this gave us a bit more control and, kind of flexibility to integrate other sensors into our own fusion block in the future. Okay, so let's see. Hopefully this works. Let's give you a quick demo. Try to Hey, there we are. Okay, great. So you can all see it. So in action, this is effectively what the computer is seeing. So this was from one of the warehouse environments that we would do our development and testing. You can see on the left is just like a steady stream of images. We would typically control the rate just to keep compute resources and usage on the drone low. On the right, you're getting the output from the entire pipeline. So you can see it's about 1 to 2 hertz, kind of slow, but you don't need that many estimates if you're trying to correct for odometry that drifts over the long run. So if you combine these two, you can get pretty good corrections and pretty good reliable execution of consistent missions over like 15-20 minute missions. There's a little bit of debug output on that you can see as well. So some confidences from the YOLO network and some of the other estimates from the POS. Okay, coming towards the end here. So challenges, lessons learned. I mean, I think, okay, yeah, we're going to finish up here. So, you guys are all, I think very familiar with this. Robotics is capital intensive. It's not for the faint of heart. Fleet management does require dedicated resources, no matter how good your autonomy is performing. Tuning and deploying this was probably the largest effort. Once you get it deployed to a location, it generally, the maintenance cost tends to plateau. It's a nightmare working with the different types of logs and things, data sources, application logs that you might have out there. So like Roboto AI, for example, great solution for us. We were looking at it towards the end, just never got to using it fully, but it's a nightmare with traditional observability tools. And obviously, the elephant in the room is that if you don't have rack structures to look at for this, the localization would fall apart, right? So we had a lot of plans to then use other pieces of the environment like the light fixtures and other landmarks in it as well. We just didn't quite get there. So this was done by a very talented team over a couple years at the Nokia Ames Scientist team, and then also some team back at Nokia Bell Labs Research. So when they watched the recording for this, thank you guys, really appreciate it. And thank you again to Drone Code Foundation and Linux Foundation for the chance to present. So. Yeah.
Thank you. Let's give them one question. Anyone have any questions? No? Okay. Oh, there you go. Is there a mic over there? This is going to look funny, me jumping on the stage on the video. Here you go.
Yeah. When you were in the phase of your sort of segmentation algorithm developing it and you were sending images to a network for processing, were you tending to send compressed images, or were you sending full resolution to whatever model would be parsing the beams to try to make geometries or masks of them?
Yeah, these were VGA resolution images, so 640 by 480, and I want to say, I can't remember if typically when you feed these things into a neural net, either I think there's a pre-processing stage within it itself that shrinks it down to like a very small, like 64 by 64, or we would do it. There was a shrinking stage. I just can't remember if we implemented it or it was
Gotcha.
behind the scenes.
Mm-hmm. And then did you find that model trained on identifying the beams, was that robust to like changing lighting conditions? Like if the warehouse had windows, if like sunlight was coming in, would like the subtle change in pixel values throw off the masking and segmentation?
It was generally pretty good. You would have to fine tune it for different warehouses on occasion. So the worst cases that we ran into were like, for example, if we would get near very strong light fixtures that weren't, kind of different than the typical layout. And then you'd also have product that would create these, features in the image that looked like structures, like the dark area between two very tall boxes looks like a vertical beam, right? You can train that out and then, kind of just only deploy that model to that customer and get it to work.
Thank you.
Yeah.
Thank you.
Okay.